Using structs to structure related data. Using structs to structure the related data. A struct or structure is a custom data type it's a custom data type, and that lets you package together and name multiple related values that make up a meaningful group. That lets you package together and name multiple related values that make up a meaningful group. If you're familiar with an object-oriented language, a struct is like an object's data attributes. An object's data attributes. In this chapter, we will compare and contrast tuples with structs to build on what you already know and demonstrate when structs are a better way to group data. We will demonstrate how to define and instantiate structs. We will discuss how to define associated functions, especially the kind of associated functions called methods, to specify behavior associated with struct type. Structs and enums discussed in chapter 6 are the building blocks for creating new types in your program's domain to take full advantage of Rust's compile time type checking. Defining and instantiating structs. Structs are similar to tuples. Discussed the tuple type section, in that both hold multiple related values like tuples. The piece of a struct can be different types. Unlike with tuples, in a struct you will name each piece of data so it's clear what the values mean. Adding these names means that structs are more flexible than tuples. You don't have to rely on the order of the data to specify or access the values of an instance. To define a struct, we enter the keyword struct and name the entire struct. A struct's name should describe the significance of the pieces of data being grouped together. Then inside curly brackets, we define the names and types of the pieces of data which we call fields. For example, listing 5-1 shows a struct that stores information about a user account. Struct user, and then fields, and then different types for different values. To use a struct after we've defined it, we create an instance of that struct by specifying concrete values for each of the fields. We create an instance by stating the name of the struct and then add the curly brackets containing key value pairs, where the keys are the names of the fields and the values are the data we want to store in those fields. We don't have to specify the fields in the same order in which we declare them in the struct. So when we create the instance of the struct, we don't need to we don't need to follow the order of these fields. And in other words, the struct definition is like a general template for the type. And instances fill in that template with particular data to create values of the type. For example, we can declare a particular user as is shown in listing 5-2. email, username active, sign count. Creating an instance of the user struct. To get a specific value from a struct, we use dot notation. For example, to access this user's email address, we use user1.email email. Oh, wait a second. Let me check. Yeah, so the order is different from this declaration. Makes sense. To get a specific value from a struct, we use dot notation. For example, to access this user's email address, we use user1.email. If the instance is immutable, we can change a value by using the dot notation and assigning into a particular field. Listing 5-3 shows how to change the value in the email field of a mutable user instance. Listing 5-3 changing the value in the email field of a user instance. Listing 5-3 changing the value in the email field of a user instance. Changing the email field. Mutable. Makes sense. If the instance is mutable, we can change it like this. Note that the entire instance must be mutable. Rust doesn't allow us to mark only certain fields as mutable. As with any expression, we can construct a new instance of the struct as the last expression in the function body to implicitly return that new instance. We can construct a new instance of the struct as the last expression in the function body to implicitly return the new instance. What? As with any expression, we can construct a new instance of a structure as the last expression in the function body to implicitly return the new instance. Oh, okay, that makes sense. Build the user and user struct here, and then in return the struct. Okay, makes sense. Build the user function that takes an email and username and returns the user instance. It makes sense to name the function parameters with the same name as the struct fields, but having to repeat the email and username field names and variables is a bit tedious. If the struct had more fields, repeating each name would get even more annoying. Luckily, there's a convenient shorthand. Using the field init shorthand. Using the field init shorthand. Because the parameter names and the struct field names are exactly the same in listing 5-4, we can use the field init shorthand syntax to rewrite build user. So that it behaves exactly the same but doesn't have the repetition of email and username as shown in listing 5-5. Oh, here user. Here's user and user function that uses the field init shorthand because the email and username parameters have the same name as the struct fields. Here we are creating a new instance of the user struct which has a field named email. We wanna set the email field's value to the value in the email parameter of the build user function. Because the email field and the email parameter have the same name, we only need to write email rather than email. Creating instance from other instances with a struct update syntax. Creating instances from other instances with a struct update syntax. Oh, instances from other instances with a struct update syntax. It's often useful to create a new instance of a struct that includes most of the values from other instance but changes some. You can do this using struct update syntax. First, in listing 5.6, we show how to create a new user instance in user2 regularly without the update syntax. We set a new value for email but otherwise use the same values from user1 that we created in listing 5.2. So creating a new user instance using one of the values from user1. User1, okay, makes sense. Oh, okay. Creating an instance from other instances with a struct update syntax. Using struct update syntax, we can achieve the same effect with less code. As shown in listing 5.7, the syntax dot specifies that the remaining field is not explicitly set should have the same value as the fields in the given instance. Specifies the remaining fields explicitly. Okay, so in all remaining fields, okay, not explicitly, okay, makes sense. Using struct update syntax to set a new email value for a user instance, but use the rest of the values from user1. Makes sense. The code in listing 5.7 also creates an instance in user2 that has a different value for email. The code in listing 5.7 also creates an instance in user2 that has a different value for email but has the same values for the username. Active and sign-in count fields from user1. The user1 must come last to specify that any remaining fields should get their values from the corresponding fields in user1. The user1 must come last to specify that remaining fields should get their values from the corresponding fields in user1. But we can choose to specify values for as many fields as we want in any order, regardless of the order of the fields in the structure's definition. Makes sense. Note that the struct update syntax uses equals like an assignment. This is because it moves the data. Just as we saw in the ways variables and data interact move section. In this example, we can no longer use user1 after creating user2 because the string in the username field of user1 was moved into user2. Okay, that makes sense. If we had given user2 new string values for both email and username, and thus only used the active and sign count values from user1, then user1 would still be valid after creating user2. The types of active and sign-in count are types that implement the copy trait. So the behavior we discussed, the stack-only data copy section would apply. Using tuple structs without named fields to create different types. Using tuple structs without named fields to create different types. Rust also supports structs that look similar to tuples, called the tuple structs. Tuple structs have added the meaning tuple structs have the added meaning the struct name provides don't have names associated with their fields. Tuple structs have the added meaning the struct have the added meaning the struct name provides, uh, but don't have names associated with their fields. Okay. Rather, they just have the types of the fields. Tuple structs are useful when you want to give the whole tuple a name and make the tuple different type from other tuples. Makes sense. And when naming each field as in a regular struct would be verbose or redundant. When naming each field is in a regular struct. When naming each field as in a regular struct would be verbose or redundant, for instance. To define a tuple struct, start with the struct keyword and the struct name followed by the types in the tuple. To define a tuple struct, start with the struct keyword and the struct name followed by the types in the tuple. For example, here we define and use two tuple structs named color and point. Color and point. Note that the black and origin values are different types because they are instances of different tuple structs. Each struct you define is its own type, even though the fields within the struct might have the same types. For example, a function that takes a parameter of type color cannot take a point as an argument. Even though both types are made up of three iterative values, otherwise tuple struct instances are similar to tuples in that you can destructure them into their individual pieces. And you can use a dot followed by the index to access an individual value. Note that the black and origin values are different types because they're instances of different tuple structures. Yeah, they are different types. Okay, makes sense. Each struct you define is its own type. Even though the fields within the struct might have the same types. For example, a function that takes a parameter of type color cannot take a point as an argument. Makes sense. A function that takes a parameter of a type color. Okay, makes sense. Even though both types are made up of three iterative values, otherwise tuple struct instances are similar to tuples in that you can otherwise tuple struct instances are similar to tuples in that you can structure them into their individual pieces. Tuple struct instances are similar to tuples in that you can destructure them into the individual pieces. Okay, and you can use a dot followed by the index of access an individual value. Init like structures without any fields. You can also define structures that don't have any fields. These are called unit-like structures because they behave similarly to unit. Okay, empty is tuple. Unit-like structures without any fields. You can also define structures that don't have any fields. Yeah, they don't have any fields. These are called unit-like structures because they behave similarly to unit. The unit type that we mentioned in the tuple type section. Unit-like structures can be useful when you need to implement a trait on some type but don't have any data that you want to store in the type itself. Unit-like structures can be useful. Unit-like structures can be useful. Unit-like structures can be useful. When you need to implement a trait on some type. Implementation useful when you need to implement a trait on some type but don't have any data that you wanna store in the type itself. Don't have any data that you wanna store in the type itself. We will discuss traits in chapter 10. Here's an example of declaring and instantiating unit struct named always equal. To define always equal, we use the struct keyword, the name we want, then a semicolon. Then a semicolon. No need for curly brackets or parentheses. Then we can get an instance of always equal in the subject variable in a similar way, using the name we defined without any curly brackets or parentheses. Imagine that later we will implement the behavior for this type such that every instance of always equal is always equal to every instance of any other type. Uh, Imagine that later we will implement behavior for this type such that every instance of always equal is always equal to every instance of any other type. Perhaps to have a known result for testing purpose. Mm, we wouldn't need any data to implement that behavior. You will see in chapter 10 how to define traits and implement them on any type, including unit-like structures. Ownership of structured data. In the user structured definition in listing 5-1. In the user struct definition in listing 5-1, we use the owned string type rather than the $str string slice type. This is a deliberate choice because we want each instance of this struct to own all of its data and for the data to be valid for as long as the entire struct is valid. It's also possible for structures to store references to data owned by something else, but to do so requires the use of lifetimes, a rusted feature that we will discuss in chapter 10. Lifetimes ensure that the data referenced by a struct is valid for as long as the struct is. Lifetimes ensure that the data referenced by a struct is valid for as long as the struct is. Let's say you try to store a reference in a struct without specifying lifetimes like the following. This won't work. Let's say you try to store a reference in a struct without specifying lifetimes. Active str. The compiler will complain that it needs lifetime specifiers. Expected and named lifetimes parameter. In chapter 10, we will discuss how to fix these errors so you can store references in structs. But for now, we will fix errors like these using older types like a string instead of references like str. Determine whether the program will pass the compiler. I32 x12 mutable and a.x plus equals 1. 1. B point y dot y1 dot a a dot x plus 1. It works. A dot x plus equals 1. And b dot x should be b dot x should be 1. B dot x should be 2. Yeah, 2. And another one, mutable p and reference init mutable reference p dot x and mutable reference to p dot y p dot y p dot x p dot y, and then dereferencing star x plus equals to 1, meaning that star x is p dot x Touch immutable reference, the reference. Then p dot x and p dot y is like a 2 plus 3. 2 and 3. Yes, got it.